Hi, let's solve now this problem using Rankine's formula. And it's a pretty simple case. We have a column, which is, let me write it in here. It is a fixed end column. And then here we have, fixed pin end column. Perfect. And it says, okay, now find what's a critical load, and also, using Rankine's formula, and consider a safety factor of 3.0. We have Rankine's formula here, which depends on the material, air section, properties of the material, and slenderness, and a coefficient that depends also on the material. As we've seen in the past, we have, this is an 8 meters length column, and then, we have most of the data we're going to need here to calculate this. So it's pretty straightforward, but it's a good example on how to utilize or use, in this case, Rankine's formula. So I have already here the formula to calculate what's at load. So it should be pretty, just, substitute the value. So, but let's do it step by step. First, I know that this is a fixed pinned column, and the length of the column, the physical length, is not going to be the length we need to use in our calculations. We know that we need to modify this length by a coefficient that depends on the endings or on the constraints of the columns at the end. So for this case that we have a fixed pin end, we know that the effective length, I'm going to call it like, L, actually, L, yeah, is going to be equal to the current length that I have. Well, let me write down the formula, L divided by square root of 2. And this is going to be equal to 8 meters divided by square root of 2, which is going to give me approximately 5,000. I'm going to transform it at once. Actually, I should at once transform it. Let's write this again to have it in the proper units. So it's going to be 8,000 millimeters divided by square root of 2. That's going to give me 5,656.85 millimeters. So the fact that I have a pin fixed column reduces the effective length or the physical length of the column to an effective length, which is going to be how much? Is about 70% of this one, more or less. Well, there you go. Now, next, we need to calculate what is called kind of a next step. We found this, which refers to the effective length. Now, they're asking for the duration ratio here, and that duration ratio is going to be calculated as, where is it? K equals to also square root of I, which is the moment of inertia, divided by the area. Now, good question is, we have two moments of inertia here. Which one should I choose? Then, definitely when you are calculating or trying to determine what's the quote unquote kind of, I'm going to tell you, that's simplistic way, what's the weakest direction you have in the column, then you have to use the one that gives you the smaller minimum or the smallest inertia, moment of inertia. So in this case, the smallest moment of inertia is given in the rotation around the x-axis. So we have here the duration ratio is 15,000 divided by the area, which is, okay, this is centimeters square. It's written like that, so we don't have so many zeros here. Divided by the area, which is 100 centimeters square. And this is going to give me 12.25 centimeters. And then if I take it to the units we should be using there, we have there is going to be 122.5 millimeters. Great. Now, I have found, length, effective length, gyration ratio, and I have all of the rest of the terms. So rest assured that we need just to substitute the values. I'm going to use the other color. It's going to see P is going to equal what? I'm going to have this strength, sigma C, is going to be 2,500, which happens to be very large, newtons per square millimeter times the area. So we have the area in square centimeters. We have to use it into square millimeters. So it's just multiplying these 2 times. So I'm going to have times 10,000, sorry, square millimeters. And then that's going to be divided, bring the ruler, by 1 plus the A coefficient, which is 1 divided by 7,500, then times slenderness ratio, square of that is 6.85, and that's in millimeters. And then I'm going to divide that by K, which is 122.5 millimeters, and this square, and this is going to be equal then to 19,465.47 then kilonewtons. If I assume a safety factor of 3, then that implies that the allowable load, I'm going to write here, it's going to be equal to this value I got here, 65.47 kilonewtons, divided by 3. Which then is going to be equal to 6,488.49 kilonewtons. And that's the answer that we were looking for. So it's pretty simple. It's pretty simple. Now, I took the time and I kind of coded in the Rankine formula and these values to get what was kind of how the graph would look like, and then how graphically this could be shown. And then if we move here, you're going to see the following results. Of course, there are certain variations in the values because, this is done by calculators and this is done, I did it in the computer in Python. So, but this is a pretty interesting graph, and let me explain it to you, break it down to you. So first, the blue line here, what you see here is the Rankine's formula. So the Rankine's formula according to this material. So I just took this formula, I input here, or started using this strength that is given here, the area that is given, the A coefficient that is given, and I just variated the slenderness of the column, from 0 to 200 and something, 240, and then I found the values of the load in this case. So, and that gives me this formula. Then it's simply saying that, okay, now you have a column with this material. Now what it changes is, okay, what's the real slenderness ratio that you have in your column? Then, okay, that slenderness ratio is about 46.19, which is kind of the results of dividing these L and K. Then if I have that, then I can just go up from the slenderness ratio, touch the curve, and that's going to give me kind of the critical allowable load according to Rankine's formula, which is this one, very, very close to what we were calculating, or I was calculating in the calculator at that time. But now, if I consider a safety factor of 3, in this case, that's going to bring me down to this green point here. So let's imagine that this is the maximum load that the column can handle, and this is the working load that we're going to have in the column by using the safety factor, and it gives me this. So it's a pretty nice representation, a graphical representation of the case. It's pretty simple, yet it's pretty powerful what we're seeing here. So I hope you liked, and it's pretty simple. I think you're not going to have any problems at all in applying when applying Rankine's formula to determine if the column is suitable for use or not. Thanks. I will continue in the next videos, talking about different formulations for columns also that are pretty interesting and pretty usable right now. Thank you.